Okay. So anyway, so we're starting a chapter, and the first chapter is on solids, and the second chapter is on liquids, and then gases. Yeah.
I think my book might be my water. Can I go do it?
You can. Okay, or you can just look up here.
Oh, okay.
Okay, so even though we had solid, liquids, and gases in middle school, and they probably talked a little bit about elementary school, even in the 10th grade, we talked a little bit about solid, liquid, and gas, a little bit, okay? But now what we want to do is, what's the physics? What's the physics of solid, liquids, and gas? You get that? That's what's going to be a little different. And so the first thing you notice is they have this picture of a geode. Does everybody know what a geode is? If you're lucky, you'll find one out in nature. I've actually found one in my life. But if you're not so lucky, you can go to these different shops and buy them online. And they kind of look like a roundish rock. But if you hit it with a hammer, they'll split open. You get something like this. And that's a great picture to start out with crystals. Now, does anybody know what a crystal is? If we're studying solids, should the word crystal come up? And I guess so, because they're showing one. What is a crystal?
Atoms.
It is. There's a pattern of the atoms. Whether or not it's in a cubic shape or 20-degree or 120-degree angle, whatever the angle is, there's a pattern of these atoms that repeats itself over and over and over throughout the whole thing. And that's called a crystalline solid. Have you heard that before, crystalline? Now, I have up here, I have a couple things. There's a couple things right there. One of those, if you were to touch it, it would seem kind of like smooth. It would be a kind of smooth feeling, and yet, if you could look real close with a microscope, you would see that it has crystals. It really does have crystals, but they're kind of smooth, you know. And there's some rocks that they even seem like glass. They even feel like glass, but they're actually made of crystals. And then sometimes you see crystals that they just pop out at you like they're really big, and you see the angles and stuff like that. There's another one. See this right here? That's kind of neat. Can you see how it's like a rhombus, almost like a parallelogram, but it's still like that? That's a different kind of material right there. Anyway, I don't know if you've ever heard this before, but when things are really, really hot and they cool off quickly, they usually form really, really tiny crystals. So tiny that it feels kind of smooth. But if things are allowed to crystallize over a longer period of time, the pattern simply builds on itself, builds on itself, builds on itself, and you can actually have some pretty big crystals like that. So the theory about the geode is that the outside cooled kind of quickly, but the inside was still very hot, very, very hot, and the heat had trouble escaping. And it slowly cooled, and it let the crystal have time to build up. And that's why you get these big crystals like that. The Science Center here in Greensboro, they actually have a gem and mineral club here in Greensboro, and they have some great specimens. I've seen crystals that are huge, just huge crystals. And there's a lot of places in South America that people will go. And does anybody happen to know what that's called right there? What that material? It starts with an A. Amethyst. Yeah, that's right. Very good. You're more likely to see quartz crystals around North Carolina. You will see. Sometimes you might see amethyst. The only reason I want to bring that to your attention is that this next page, when they talk about crystal structure, how do we know that things had a crystal structure to begin with? Believe it or not, we actually have machines that can slice a rock into a thin section. Did you know that? They can actually cut a rock into a thin section. And people like to do all kinds of things with these thin sections. Maybe they're going to shoot x-rays at them. There's a microscope you can use. It's called a polarizing microscope. And what they do is they have these filters, and you simply rotate the filters, rotate, and all of a sudden the slice of crystal starts changing colors. And they can actually use that to identify the rock. So if you become a geologist, you'll have these little samples, and it'll say, under polarized light, this is what that looks like. Hey, what kind of rock is that? Let's take a sample. Yeah, that's what it is. So they can actually identify it by the pattern of polarized light, or they can do something like this. This happens to be what happens when you shoot x-rays at it. It kind of gives this little pattern here. I don't have an x-ray machine, but I do have a laser beam, okay? So I have a little laser beam. Everybody see that? So what I thought I would do is, I thought I would shoot it right through this crystal and see if I can see anything with that. So let's try it. I'll put it right next to it. Everybody see anything? Okay, not very exciting. Okay, not very exciting. Let me try it from a longer distance. Anything? No, not very exciting. So why did I even get this out? Why don't I turn it on its side? Let's try that. Whoops, my finger out of the way. Oops. What do you see here? Now, something in that structure, there's something in that structure. Can everybody see that? Yes? There's something in that structure that's making that beam be split, isn't it? And what if I turn it this way? Is it going to be the same pattern? Now, all I'm trying to tell you is there's something about the way these particles are arranged that gives me a different pattern of scattering laser beam, isn't it? And same thing would happen with x-rays too. It just so happens this is called a optical calcite or fluorite. And have you ever seen this? You ever seen what this can do? Okay, what you do is you put it on some, like a letter, and can you see this? Do you see how the letters, if I had a regular rock, you wouldn't be able to see it, but see how the letters are brought up to the top here? That's kind of hard to see, isn't it? How about that? So we can see through it, but you'll actually, what will happen is, this will actually usually give you two images. I'm not seeing it. Let me try it again. But it'll actually give you two sets of letters as you're looking through here. And that's what happened to that beam. It kind of splits it in half like that. So you look at it a certain way, it'll make everything double like that. Okay. Let me make sure I got the name on that right. Yeah, optical calcite. Optical means it's clear enough that you can actually pass light through it, stuff like that. Now, what another thing we talk about solids, and this right here is the most common solid for you is sodium chloride table salt. And table salt, if you were to let it take some salt water and let it just evaporate slowly, you can get some fairly big crystals. And those crystals, though, will be cubical. So some crystals are 90-degree angles, and NaCl happens to be one of those, and they figured out the structure of that. And then I've seen other crystals like this one, the one I just showed you. Notice that those are not 90-degree angles. I don't know if you can see that very well, but they're not 90-degree angles. It's at an angle like this. Can you see it? Now, what I think is always interesting is that God does this all the time. We just sometimes don't figure it out. Sometimes, if you're really good, you can look at clouds and actually tell what's going on with the air there. You ever seen that? Sometimes they look at clouds and the bottoms are absolutely flat. Have you ever seen that? Well, that tells me that the temperature right there, if you go there, it's warmer. It's warmer. It's cold. If you go up here, it's colder than it freeze water up here, and it's colder here. So it tells me exactly what's going on. Or sometimes you'll see wispy clouds. Or sometimes you see clouds that are like cumulus clouds. And it kind of tells you what's going on with the air. Usually cumulus clouds are air is rising, and it keeps throwing moisture, and it kind of builds like a billowy thing like that. And what I always thought was interesting, though, is that God said, hey, you know what? When you look at that sodium chloride crystal, and it looks like 90-degree angles, you know what's really going on in that tiny, tiny world down there at the size of atoms? What's happening at the atomic level? And guess what's happening at the atomic level? 90-degree angles. It's like the crystal's shouting at me. I'm trying to tell you. I'm trying to tell you about me way down in the little world that you can't visit. You're just not listening. And what about this crystal here with the angles? Look at that angle there. What are they trying to tell me here? At the atomic level, what kind of angle is there between the particles? It's the same, isn't it? Well, that's what I think is always fascinating. I never knew that when I was your age. I never even thought about that kind of stuff. And so when you see a crystal of quartz and it's like maybe you see a 60-degree angle or something like that, that's what's happening at the atomic level also. So I always thought that was kind of neat to think about that. I also remember I was when I was in college, I went to the biology building pretty often, and down in the basement, I don't know, sometimes I like to explore. Do you ever do that? I like to explore. So I go down there and see what's going on there. And I saw this, this guy there once, and he was just getting paid. So I don't know if he was a real science student or not. I think he was just getting paid to do it. So, and here's what they did. They had a piece of paper, and they said, I want you to take whatever's on the piece of paper, and you'll see these little things that look like that, and I want you to paint that onto a piece of glass. So this piece of glass was about this big and about that wide. So he had the paper, he measured, and he painted, and he made a nice paint, just the right size here, and that was supposed to be small, and that was supposed to be, anyway, he painted that like that, and then he went over to on the wall, there was a rack, and the rack had little pegs out here, and he would slide glass number 1 right there, and then he would start another one. And I'd come back a little while later, and there was about 50 of these. So he had to do 50 pieces of information on a piece of glass, and they were all had a little bit of space between them like that. Glass plate space like that. Well, then I had no idea what they were doing. I had no idea what they were doing. What they were doing is they had discovered these things called proteins. Remember way back in 9th grade, proteins? Proteins are made of amino acids, and they have these structures, and the structure of the protein has everything to do with how it works or where it doesn't work. Well, they actually want to know, how are these atoms connected to each other? How is the carbon connected to the hydrogen, et cetera, et cetera, et cetera, et cetera? If I could only see it, how can you see a molecule? It's hard, it's too small. Well, they would shoot x-rays at them, and they would shoot them like this, in different layers. See that? And this is the interference pattern like that. That was what happened. Say, I hit it, I didn't hit it. And they had this drawing, and what was so neat, and this was neat for me. Okay, so he had some light bulbs. So he had some light bulbs, and when you turn it on from the below, light would shine up to the whole column. And then all of a sudden, I understood what they were doing. Now imagine these glass plates really, really, really close together, okay? Can you imagine that? Okay, now imagine one of the plates looked like that, and the one above it might have a little bit bigger circle, and the one above it might be a little bigger, and then a little smaller. And what was happening is they were drawing the atoms. And so a three-dimensional orange, if I took an orange and sliced it, wouldn't the first slice be a little circle? The next slice would be a bigger? Well, that's what they were doing. And when they turn that light on, you can stand back and you can actually see, an atom here and an atom here and here. And you could actually, if you wanted to, you could measure the angle between those atoms. Now, I don't know how humans figured that out, but they did, didn't they? They said, we're going to figure out the shape of that molecule, and how do you do that? And that's what they thought they were doing. And so it was really pretty neat. When I saw them turn that light on, and I saw them, and all these things were like I could actually see the structure of that protein molecule there. Okay, so there's a lot of neat things they could do with solids. Let's go to, by the way, I'm going to show you today because I haven't figured out which one. There's about 3 videos. I have to pick the right one, so I don't want to show you 3 videos. But does anybody know, and if you have your book with you, I'd like you to write that word in there. What about solids that don't seem to have a repeating pattern throughout them? Or they may have a little bit of a pattern, but it's not throughout the whole thing. Or they have no pattern. What do you call a solid that is not crystalline? What is it? What name is used to say you really don't have a pattern to you? Does anybody know that? That's right there, but and it's called amorphous. And I've never taken Latin, but I do know that morph means shape or form. Is that correct? And you put an A in front of it, that means no shape, no form. Isn't that right? A in front of words. Right? Remember in 9th grade, P-T-E-R-A meant wings. Isn't that right? Coleoptera. Did you know that P-T-E-R-A meant wings? but fleas. What were the order of fleas? Not Siphonoptera, Siphonaptera. What does that mean? No wings. You're a siphon with no wings. How's a flea? Okay. Anyway, that's what they call it, Siphonaptera. Anyway, so this right here, amorphous solids are things like putty and rubber and even glass. Certain glass is what they call amorphous. Unless you buy the really, really expensive glass. Has anybody heard of crystal glass? Ever heard of that? That is glass that actually does have a pattern to it. And so, anyway, so glass is amorphous also. All right, well, let's go to something you actually already know a little bit about. The author thinks maybe you haven't done density yet, but you have. So what I'm going to do is take you just a little bit further, in this idea of density. And you see how I wrote in my book. And what I would like to do is use the idea of density to teach you something more important, okay? I'm going to use density as my vehicle. Get inside, get in the car, let's go. I'm going to take you on a little trip here, and let's see what we can do with this thing. All right, well, here's the equation. Density equals mass divided by volume. Is that correct? That's my definition. And what I'm going to do is I would like you to think conceptually about this equation, then I'll take you a little further with this. I loved that some of you on the last test did this. You said, I'm going to plug in some numbers and see what happens. For example, I want to be nice to myself. D equals M over V. I think M is 10 and V is 5 because, those are easy numbers. So what is density going to be? 2. Now the question would be, what happens to any object if the mass stays the same? So keep that number the same, but the volume goes down to maybe 1. What's going to happen to the density? Okay, the density is going to, whoa, look at that. Now watch, it's even better than you think. How many times smaller did I make the volume? And remember, Mr. Short, Mr. Tall, you should not be thinking about 4. Do not do that. If you're in the world of ratios and proportionalities, when I say, tell me about 5 and number 1, tell me about the number 5 and 1. You say, well, 5 is 5 times bigger than number 1, and what else? 1 is what? One ratio would be 5 over 1, wouldn't it? What's the other ratio? Okay, and did you know that number 1 is 1/5 of the size of number 5? Okay, now, so watch what happens here. If you keep the mass the same and you make the volume 5 times smaller, I made it 5 times smaller, what happens to the density? It went from 2 to 10. What does that do? Don't say 8. What is it? It went 5 times bigger. One more time. I made the volume get 5 times smaller, and the density got 5 times bigger. So what I'd like to do is take you somewhere with this a little bit, and I'm going to take this equation and I'm going to take it out of the fraction zone. So now I rearrange it so it says D times V equals M. Now I'm doing this to help you, okay? All right, I'm going to show you that in all of physics, in all of math, in all of anything, if you see an equation that looks like this, if you see one of these variables on one side and one on the other, and nobody's being squared or square rooted, you can say this. How is density, how is volume related to mass? And here's what you say. If density is held constant, so don't let it change. How is V related to M? They're called directly proportional. Now, directly proportional is something you actually understand very well. Directly proportional means if you get 2 times bigger, I get 2 times bigger. If you get 5 times bigger, I get 5 times bigger. You actually have seen that when you did your graph. When you did a graph like this, you had mass and volume. Remember that? And X kept getting bigger. and y kept getting bigger, didn't it? And you got a straight line. A direct proportionality always gives you a straight line. Now, what does that mean? Is anything constant here? I know you guys are a little bit tired, David. Is volume constant? No. Is mass constant? No. Is there anything that was constant? There is. It's that world you don't want to get into. What is the slope of the line here compared to here, compared to here, compared to here? A straight line only has one slope. How is that possible? It's a ratio. If two things are directly proportional, the ratio of them is a constant. I'm going to say it again, okay? One more time. If two numbers are directly proportional, and if you do an experiment and you get a straight line goes through 0, 0, if they're directly proportional, here's what you can say. If volume gets 10 times bigger, the mass will get 10 times bigger. You get that? That means they're directly proportional. What about if you saw them in an equation? Well, you'd see one of them on one side equal sign, you see on the other side equal sign, that they're directly proportional. If what? If you hold that constant, right? But let's rearrange this a little bit. Ready? If d times v equals m, then what is m over v? That's density, isn't it? Now watch. You told me that the slope was constant. And what is the slope? What is the slope? Isn't it y over x? And what is y over x here? M over v. And what is m over v? And in this case, m over v is constant, isn't it? So what can you say about a piece of metal like this? And if I had the mass and the volume, and I cut it in half, and I had the mass and the volume, and I cut that in half, and I found the mass and the volume, and I kept doing it, and I had a whole graph. What would the graph look like between mass and volume? It would be a straight line through 0, 0. You say mass and volume are directly, what's the word? Directly proportional to each other. That means that if the mass gets 3 times bigger, the volume gets 3 times bigger. Is anything constant, though, about this piece of metal? What is it? If I cut this into pieces, is there anything constant? The ratio, and that, you're right. What is the name of the ratio? Density. The density of any piece of aluminum is always the same number. You get that? And we've kind of had that. We had a little bit before. But now I'm going to show you, look at this equation again. If these are directly proportional, as long as what? This is held constant. Well, what is m over v? It is constant. Density is constant. All right. What do you think about that? Now, we had one, I did this last chapter, F equals ma. This is Newton stuff. Force equals mass times acceleration. Now, let's do an experiment. Put you in a vacuum. How much do you weigh? That's a force on you. And what, let me do another one. Hang on. Let me do another way. Sorry. Let's go back up here. Sorry. Yes. Yeah. I'm sorry. I skipped ahead a little bit. If two things are on opposite side of the equal sign, if everything else is held constant, then they're directly proportional. But what if two things are on the same side? What if they're on the same side of the equation? What would it look like? And this graph would look like this. I see that curve right there? We're going to get into this a little bit more. This means that they are called inversely proportional. You say, well, what does that mean? Okay, if you hold this constant, and if this goes up, this has to go down. What was it when it was directly proportional? If this went up, this went up, didn't it? If this got 2 times bigger, you got 2 times bigger. But what if it's inversely proportional? What if volume gets 5 times bigger? What's going to happen to density? It's got to get 5 times smaller. Now, if that doesn't make sense to you, look at the example we did a while ago. Look what I did the equation. What I did is I let mass stay constant. That means I must have been investigating volume and density, right? And I let the mass stay constant, and the volume went down 5 times smaller, didn't it? What happened to density? It went from 2 to 10. What was that? 5 times bigger. Now watch. Look up here. If mass is held constant, how is density and volume related? They are inversely proportional. Some books say indirectly proportional. Same thing. What does that mean? What if volume gets 3 times bigger? What happens to density? 3 times. They're inversely proportional. 3 times bigger, I have to get 3 times smaller. Does anybody know what another way of saying 3 times smaller is? 1/3 of what used to be. Are you with me? I know you're tired, right? Okay, I know you're tired. Now, so I'm using density because you're kind of familiar with density. You're kind of familiar with this graph, but I'm trying to show you about this thing called inversely and direct proportionality. This is another example we had before. In a math book, it says that the circumference of any circle is equal to the diameter times pi. Is that correct? How is circumference and diameter related to each other mathematically? Are they on the same side of the equal sign, or are they on opposite? Okay, they're on opposite, right? And as long as this is held constant, the good news, it is. If this is held constant, then what kind of graph would you get if you made a whole bunch of circles with a bunch of diameters, and then you measure diameters and circumferences? What would it look like? A direct proportionality. Now, what does that mean? If the diameter got 5 times bigger, what happens to the circumference? 5 times bigger. What kind of graph do you get? This. What's the equation look like? Circumference and diameter will be on opposite sides of the equation, and there'll be some kind of a constant here. The constant goes with this, because remember in math, y equals mx, remember that? So if I do this graph like this, it'd be c equals m, which is going to be pi in this case, c equals pi times diameter. All right, anyway, I thought I would just use the idea of density to show you some things, and I'll do one more example to see if it makes sense to you. This is an equation that you might see if you stay in science and take chemistry long enough. It's called the combined gas law equation. It says PV equals nRT. Now, I've never taught that to you before, ever, right? Ever. But you already know, right now, you already know something about that equation. Tell me about how pressure in a gas is related to temperature. And I'll do the first. Oh, you want to do it? Good, thanks.
As the temperature goes up, the pressure goes up. Because
Proportionally or not?
proportional.
So if you made the Kelvin temperature get 2 times bigger, what would happen to the pressure? These are on opposite sides of the equal sign, aren't they? If this gets 2 times bigger, that's what you said, what would happen to pressure?
Well, if they're on opposite sides, so it's a direct relation.
It's a direct proportionality. It's not just a direct relationship. It's a very special one. So if this got 2 times bigger, what would happen to the pressure?
Should go up 2 times.
How much?
2 times.
2 times bigger. Is that everything? Now, he left out one important thing. That's assuming that all the rest of these are held constant. You get that? Now, believe this. Imagine you had a container and had air in it. And the volume, it's a really solid container, so I'm not going to let the volume change. And this is the number of moles in there, and I'm not going to let any gas in or out, so I'm going to keep that constant. And this is just a number, it's a constant like pi. That's not going to change either. So none of these are allowed to change. And I got this container, and I heat it from 100 Kelvin to 200 Kelvin. I made the temperature 2 times bigger. What's my pressure gauge say? What if it said 5? What would it say now? The temperature got 2 times bigger, and the pressure started at 5. What's the new pressure going to be? Uh-oh, I thought I had you on this one. I thought you had this one. What if they're directly proportional, If you make this 2 times bigger, what happens to P? Okay, so I got this container. I heat it from 100 to 200 Kelvin. I just made the temperature 2 times bigger. What happens to the pressure in there? Pressure started out at 5. Let's say it started at 5 atmospheres of pressure. What's it going to be now? 10. I've never taught that to you before, but this is a tool. This is one of those learning tools. You could use this for any equation you ever see, for anything. All right, I'm not sure I've convinced you of this. Let's do another one. Let's do one more and I'll move on. How is pressure and volume related to each other? Elon, let you do. You look like you picked up on this. How is pressure and volume related to each other? They're on the same side of the equal sign.
Well, as long as the volume stays the same, then the pressure would stay the same, like with everything else.
Wait now. If I'm going to study these two, I'm going to allow these to change.
Yeah, but if volume goes up, pressure goes down, and if pressure goes up, volume stays the same.
Proportionally or not? And yes.
Yes.
So if you were to make, if you made the pressure go up 5 times, 5 times the greater pressure, what would happen to the volume?
Stay the same. Oh, no, go. Sorry.
I'm going to let all these stay the same, but if I want to study these, if I start changing the pressure, it'll change the volume. Now I have to have a container that the volume can change, like a balloon.
Yeah.
Let's give it a balloon, okay? And it has a certain amount of pressure, and it has a certain volume. What if I put 5 times the pressure on that balloon? What's going to happen to the volume? The pressure got 5 times bigger. What happens to the volume?
Goes down.
Keep going. How much? 5 times smaller, right? What's another way of saying it got 5 times smaller? Use a reciprocal of 5.
1/5 the size.
Yes. It went to 1/5 of its original volume. Now all I'm doing is I took density and I took the idea of direct proportionality and showed you about that. And then I also did a thing called inverse proportionality. You get that? You would say that pressure and volume are inversely proportional to each other if what? If all these are held constant. What kind of graph would you get? What do you think, Eli? What would a graph look like? Would it look like this? A P and V?
No, because pressure goes up. If pressure's on the X, the volume's on the Y. When pressure goes up, volume goes down.
Right. As a matter of fact, it would give you this classical inverse proportion curve. See how it curves like that? So anytime you do something that's inversely proportional, you'll get a graph that looks like that. If directly proportional, it'll look like that. What do you think? All right. Now, guess what happens? Because it's possible that you're only taking in part, because you took the pre-ACT today, it's possible that not all this is sticking, right? Is it starting to stick at all? Anyway, I'll go ahead and do this. I'll do it again, but not today, because you don't want to do it again. Let's go over to the next one. We looked at this chart before, didn't we? Remember the density chart? Okay. Did we, what if you found something that looked kind of like gold, and you want to know it was gold? How could you bring it in here? Could we tell if it was gold in here? And we should be able to. Gold is one of the super dense materials, right? So we could find its mass on a balance, find its volume by probably water displacement. We could do that, right? Mass divided by volume, give you density. But it better be up there. This is really dense, isn't it? Isn't that right? Now what I have today, and I'm hoping that you are awake enough to do this, otherwise I don't want to get it out. I'm going to get something out which, show you what I'm talking about here. I need to get a tub. Go get a tub. All right, so what I'd like you to do, even though you think you understand what something dense is, I don't have any gold like that, but I have something that is down here. There it is. I do have something that's about 13.6 grams per cubic centimeters. I have mercury, okay? Now, before I do this, I want to talk to you about it. Number one, I have done lots of things with mercury That's why I'm so weird. No. I put it in my hand, but you're not allowed to do that, okay? For whatever reason, once you get the public opinion against it, everybody thinks if you look at mercury, something's going to happen to you. So I will tell you that there are ways that mercury can kill you. That's for sure. There is a way that your car can kill you, for sure. I would never vaporize mercury and breathe it. Vaporize mercury, that's not good. I wouldn't want vaporized mercury to go into my system. I wouldn't like to get it in my system at all. Get that? And I will tell you that most of the bad press of mercury has to do with not mercury the metal, but mercury the ion. And that could be in a compound like mercury chloride. Now, mercury chloride, if you put it in water, it dissolves and you can't see it anyway. And yet those mercury ions, if they were to get in my system, and I have a lot of water in me, I'd have mercury ions all over the place, and that would probably not be good for my organs. And my organs don't like heavy metals. They don't like cadmium. They don't like copper. They don't like zinc. There's a lot of metals that I shouldn't have a lot in my body. See that? Besides mercury. So what I like to do is, if I let you touch the bottle, not mercury, and I don't want your parents to come in saying, what? Okay. So here's what I do have. I do have a test tube with a little bit of mercury in there, and if you want to just kind of make it go back and forth, and that'll wake you up, you can do that. The old name for this, what's the old name for this? Quicksilver. All right. They even has some rock groups that Quicksilver messenger. Anyway. So Quicksilver was, if you tried to pick it up, you just couldn't ever pick it up. It'd always be outside your reach. So here's the first thing you have is a little mercury in that, so you can see it. There you go. And then the second thing is we have a little bottle of mercury. And what I'd like you to do is you have to follow the rules, or else you can't do it. I'd like you to take just these two fingers here, okay, and I'd like you to try to pick it up. And so what I'm going to do is I'm going to keep it in this little foam container. And what you do is just pick it up here, and you'll think, well, I picked up a water that big. So anyway, just pick it up like that. But I'd like you to keep it no higher than this right here. Get that? Don't bring it up to here. Just bring it up like about to here, and then lay it down real quick, gently like that. So I'm going to put this back here and let you, if you want to look at that. So why don't we take anybody in the first row? You come back here first. And if you don't want to do this at all, you can, but if you want to look at the tube of mercury, here's this one. And the second thing is, if you want to try to pick it up with your thumb and little finger. So, anybody in the first row? Come on over. Volunteer.
Word.
Alright, so, have you seen mercury before?
Yes.
Okay, where did you see that?
I don't know.
Okay, you had to take like this, only lift it about this high, okay? Take your thumb and little finger and pick that out. Now, the reason I do that is,
Oh, you said.
Yeah, that's your little finger.
This?
yeah, no, not too high. There you go. Okay, what do you think? WQ's out, what happened?
No.
No. It's quite a bit heavy for WQ's out, right?
Yeah.
All right, put it down gently. Anybody else in that room? All right, come on. So have you seen mercury before? Okay, so it looks like this. And it's in mercury thermometers, but they a lot of times don't sell these anymore. They don't sell mercury thermometers anymore. In fact, I got some of this mercury, they stopped because of bad press. It used to be when they took your blood pressure, there's always something on the wall, and it had this silver bar that would go up when they pump air in, right? And it was a mercury sphygmomanometer. And everybody had, all the doctors had it on the wall, and that's how you did their blood pressure. Mercury gets a bad name, people don't want mercury, go ahead. They don't want mercury anymore, and so then they had to use the digital. Now they have the digital blood pressure things, and everything's electronic. What do you think? Pretty strong. But that's pretty heavy, wasn't it? Anybody in the second row, you want to try it? Now, so what happened is some of the doctor's offices and hospitals, they had to get rid of it, and they actually charge you a lot of money. Companies charge you a lot of money to take care of mercury the right way. And so some doctors, I got this over 30 years ago, so I don't even remember the name of the doctor, but he gave me quite a bit of this mercury. And, I said, we're gonna use it for school, okay. And, so now I have it, and he didn't have to pay to get it, take your test. Anybody next row, let's try it. All right, go ahead. So if you thought that you knew how dense gold would be, this is not even close to gold, it's only 13.6, isn't it? So imagine if that were gold, it would be even harder to lift. All right, next row. It would be even harder. Anybody, it would be even harder to lift it up if it were gold. You might have trouble lifting it with your little fingers.
Aren't vacuums still measured, or not using mercury, but the unit is inches of mercury?
Okay, now, when we get to the chapter on pressure, the bad news, you're gonna find out there's about 5 different units they use for measure. One of them, when they do storms, all of your weather forecasters, they still measure in what they call inches of mercury.
Knows how far we're down, isn't it? Very.
So, the atmosphere, the way the atmosphere can hold up a column of mercury like 30 inches tall. And we'll talk about that. So they still do use millimeters of mercury, inches of mercury. All right, next row. Now you can probably lift that and compare it to that. That's easier to lift than this. All right, anybody else? Sure. I'll have it here, I will have it here if you decide that you wanna look at it tomorrow or the next day, you can do that. One thing, I did this one time when I had to put it in here, you have to be extremely careful. I had this bottle, pretty big bottle of mercury, but you just don't sit here with a beaker and go like that, like water. If I were to go like this, it would knock the whole beaker out of my hand. It would be difficult. So I had to kind of brace the bottle in with my body and go like this, but I didn't want that thing to slip through my hand like that. And so pouring liquids like this is really, really difficult. Tell you a quick story about mercury. Does everybody know mercury is a metal? Okay, and it's really the only metal that's a liquid at room temperature. And so if I put a battery on a light bulb and 2 wires, it would conduct electricity and something like that. I had when I first started teaching my first year, I was a friend, and I was actually the biology, environmental, what else did I do? Yeah, maybe a little chemistry teacher. Another person was a physics teacher, okay? But anyway, he was my age, and he actually bought a used boat. And we're all right, on the weekend, let's go get the boat, take the boat out on the lake, okay? He'd never had a boat before, but he knew he wanted to buy a boat, so he did that. And so we went out there, and he took it off the trailer, and then he's trying to start it. He can't, it's not the electric start, he's trying to start. It won't start. He takes it back to the guy, he just bought it from him, right? He said, I can't understand, I can't get that motor to start. The guy takes the motor, he puts it in a bucket of water, big tub of water, okay? And what he did was, he took the motor and he cranked it down here, like instead of the motor being like this, he put the motor like it would have been. And it started right up. And my friend kind of felt kind of silly. I had never heard of this either. It had a thing called a mercury switch in it. And a mercury switch means that I don't want you starting the outdoor motor when it's like this. Because you know how I'm cooling, how the outdoor motor gets cooled? It takes water from the lake to cool it off. It's not in the lake, you see? So we're gonna put a little mercury switch in there, and when the thing's at an angle, the little piece of mercury is gonna go down like this, or gonna go like this way, and you won't be able to start the motor. But if you put an engine like that, the little piece of mercury will go like this, and you'll be able to start the engine. And I never heard of it. It's called a mercury switch. Has anybody ever heard of that? Anyway, so mercury switches work on angles. If it tilts, it starts. If not. All right, well, thank you. I know you're tired today. Thank you very much for your attention. But if you have a chance to start looking at the book or maybe doing some of the drawings, you can do that.
I have studied Study hall.